I also thank very much the organizers for inviting and allowing me to say also something about our work in fuel cells. It has been a very busy gas week from my side, because in fact yesterday I was in Brussels at ENGIE, and where we have a joint EU project with them, and it was interesting because this gives a link to the talk from Statoil Equinor that we have seen before. There was a site, a technology center on the CO2 capture and valorization, and in fact one of the things that was reported is the measure of the impurities in that CO2, because this is one of the things that we do. It's electrolysis of CO2, so that is in collaboration with ENGIE. And then 2 days ago, on Wednesday, I was in Amsterdam at Shell, and there we have another joint EU project which is on the 3 generation, which was just mentioned on the slide before from Mr. Mouraki. So 3 generation is the use of fuel cells of the solid oxide technology to alternatively switch between modes of power generation, power and heat generation, power heat plus hydrogen generation, then coupled with fueling stations. So I'm going to talk about fuel cells, about solid oxide technology, actually not only fuel cell way, but also the electrolysis way. So fuel cells is just the overview of the technology. They come in different shapes and sizes and families, and associated with that is operating temperature and then also the use of fuel. And typically what is done is that we either transfer hydrogen from one side to the other, from the fuel side to the air side, in form of hydrogen of protons, or we can also transfer oxygen from the air side to the fuel side. It's an electrochemical principle. We never mix the fuel and the air directly, and with temperature also the efficiency goes up, as you see here. And this is the focus of our work. We are into solid oxide technology, reaching now 60% net efficiency, and that is in combined heat and power systems. So a little bit more on the operating principle. So if we take those two main representatives, if you so want, on the right-hand side, this is a cross-section. So there we have a membrane of a polymer, and which transfers hydrogen. And so here only hydrogen is used, with the exception of methanol for some portable applications. So here we talk about the mobility. This is the fuel cell cars that I'm sure you're all very familiar with. Then on the left-hand side, there we have high temperature operation. This is based on oxides, on ceramics, where we transfer the oxygen from the air side to the fuel side, producing steam and CO2, which also gives us the interesting opportunity to easily separate out the CO2. And here we would run on natural gas, biogas, syngas, ethanol. In fact, I say here this is stationary application, this is a mobility application. In fact, Nissan has now managed to also embark a solid oxide, a ceramic fuel cell, onto a car running on ethanol. So the interesting thing of the solid oxide technology is that it works both ways. So the slide before, as you have seen, that was fuel to electricity. Here we go electricity to fuel. So here we apply, we inject the electricity and we make the fuel. So we inject also steam and or CO2, and we will extract hydrogen and carbon monoxide, which can then be further synthesized to methane. And in fact, the polymer technology is not directly reversible. So you need a different device to do that, because of the catalyst, because of the fact that you are in a liquid medium. So here, some demonstration of what we've measured in our lab. This is also an ongoing EU project called Balance. This is in the perspective of grid balancing. So here we are doing, this is lab work, this is a cell tested from one of our partners, and so you see here, this will be the fuel cell characteristic, voltage, current, and this is the electrolysis characteristic, so where we apply, and so it goes obviously in opposite ways. And here we have been cycling between this at around 0.75 amps per square centimeter. And so you see that after some burn-in, or some forming of the catalyst, after a number of cycles, we basically go back and forth between these two modes with exactly the same device. And electrolyzing at 1.3 volts, I always get suspicious remarks when I say that, but it is 100% efficient. That's just simply given by thermodynamics. If you electrolyze water at these temperatures, steam rather at 1.3 volts, you are recovering 100% of your electricity, of your electrical energy, into chemical energy as hydrogen. So here, a very simple comparison of why electrolyzing steam is so interesting and is so efficient. So this is the classical liquid electrolysis, where you would typically need about 2 volts. The polymer technology can be operated in the other sense, as I mentioned, but with a different device, not with the same device as you would use in the fuel cell. You can develop interesting current densities, but you also need to apply at least, say, 1.7, 1.8, 1.9 volts. With solid oxide, we can start the electrolyze at 1 volt and below. Okay, and current density, that would scale, that correlates with the cost of the catalyst, and efficiency goes in this direction. So we actually are more and more efficient when we use lower voltages. This is probably the one take-home slide message of the interest of fuel cell technology. So this is a commercial system. This is from our industrial partner Solid Power, which is now being manufactured in a plant in Italy. These systems, there are now thousands of these installed across Europe. So the stack, there's a 2 kilowatt stack who goes in here. There is some balance of plant in there, heat exchanger, control, etc. And this goes into this box, which looks like a dishwasher or a washing machine, which you basically connect to your gas in your cave or in your technical room, and you have your own power plant at home. And so you are 60% efficient over a fairly interesting range. So you can modulate power. You can also get, instead of 2 kilowatt, 1 kilowatt, and you're still at the same 60% efficiency. And this compares with turbines or engines, which I've taken from certain references where the part load efficiency is always lower, and also the overall efficiency. We set the world record in our lab on a short stack from Solid Power, going up to 75% DC efficiency. So 3/4 of the chemical energy of methane is converted into current. It's not only about efficiency, it's also and more so about emissions, about the cleanliness of the technology. So this is taken from one of our recent papers in collaboration with colleagues. And so here you see micro turbines, you see internal combustion engines. This is the power size, and this is the LHV, the electrical efficiency of the technology for different published data. So you see it's not always 60, this would be us here. But the other technology, generally speaking, it's always above 50. This would be molten carbonate. And here you see the NOx, okay, the associated NOx emissions for combustion engines. And milligrams per cubic meters may not say very much, but if you take this here, if you take a 100 kilowatt system, an engine with 37% efficiency will emit 1 ton of NOx a year. An equivalent fuel cell emits less than 10 kilograms. This is just the status of worldwide development as it's been going on over the last couple of years. So on the left-hand side, this is megawatts shipped of the different technologies, so which I did not cover all. We would be in green here. Solid oxide, you see polymer electrolyte is dominating because there the supply chain has already reached the market, so there is standardization of components, there is cost reduction, and there is a lot of drive, of course, from the transport sector there. But you see that the SOFCs are on the increase, and especially, as was mentioned before, Japan is again extremely pioneering in this with NFARM program, which now has already deployed around 250,000 of micro CHP. So these are 700 watt units placed in houses, in apartments, 50% net AC efficiency and 40% heat. which are now costing around 10,000 francs a unit and coming down in the next few years. And they come from 20,000. So this is due in part to the volume manufacturing. This I wanted to skip. I did not want to talk about that in the interest of time. If you have questions to biogas, we can also do that. So I'd like to come to this slide here. So this brings us back to electrolysis, where we have an integrated system approach in collaboration with my good colleague François Maréchal, also from EPFL Sion. So what we consider here, what we compare is steam electrolysis and co-electrolysis, so steam plus CO2, and then with downstream methanation. And this would be a Pareto optimization. What we show here, this is methane yield, this is system efficiency. It's demonstrated here that theoretically we can reach with this power to gas route from electricity to methane, that we can go above 80% efficiency, which would be the highest for power to gas route. And we have a good collaboration here in another EU project called Pentagon with our colleagues from Rapperswil, the Fachhochschule, with Professor Friedl, our colleague, also being here. And we are together, we are setting up an installation now in Rapperswil, which hopefully will be later in this year demonstrated, where we deliver the solid oxide side and they on their side deliver the system, including the methanation part. I conclude with this. This is our lab. What do? We have a lot of characterization equipment. We do a lot of modeling in parallel to that. I'd just like to maybe come to some take-home messages. So I hope I was able to show you that fuel cells are reaching the market. So micro CHP units, but also cars and buses has been mentioned. 60% efficiency net in a system is a fact. It's extremely clean. Japan is leading the way in micro CHP. In the US, there's also a lot of distributed power generation. There's multi-hundred megawatts deployed now, but in larger systems. Importantly, China has entered the game, and this is gonna make things move, and also in Europe. And the prime driver for China is, of course, efficiency is also there. It's intrinsically there with this technology, but it's especially about pollution. So there is a huge incentive in the transport sector to replace diesel buses with fuel cell buses. I had no time to talk about biogas. Solid oxide electrolysis is extremely efficient. And the technology is truly reversible, which is not the case for the low temperature fuel cells. And with that, I'd like to thank you for your attention.
Thank you very much. Any questions?
Hans Wach from Gazprom Midland. My question is, what is the stability of the stack? Does it work also in longer term or many hours, or is there some kind of loss of efficiency?
If I have the slides, I'm not sure whether it is included. I had one, but maybe.
Just orally will do.
Yeah, unfortunately, I don't think it's. I had supplied this, but unfortunately, it's not there. No. The system that I've been talking about, the Blue Chain, the 2 kilowatt from Solid Power, it's been deployed now since a number of years. There are about 1,000 running, and we have a return on the running of the systems now that once some have reached 3 years, and there is a loss in efficiency of around 2% per year. So after 3 years, we start at 60. After 3 years, we are at 56%. So there are degradation issues. This is very well known. This is for any new technology the case. This is also for the low temperature fuel cells. This is for batteries. This is in any technology. This is where a lot of progress has been obtained in the last years. In Japan, in the NFARM system, there is a return on the operation now for more than 5 to 6 years. And there I know that some of the systems there they have an efficiency loss of 1% per year. So you start at 50 and after 5 years you are at 45%.
A quick question. You mentioned in your last slide that the biogas can be directly used in SOFC. What about trace components and the problem of the unwanted products in biogas?
Yeah. So this is why, I mean, we've done quite a number of studies on trace contaminants in biogas. This is obviously a very good question. It's the same also for natural gas. We also have sulfur in there. Sulfur is definitely something that you have to take care about. It's not only for fuel cells the case, it's for any downstream technology, because sulfur just loves any metal and sticks there and will just do harm to any type of catalyst. So we know what is in the different biogases, we know what they do to our catalysts, we also know how to take them out. And this is also an extremely exciting field, which is also booming. There is a lot of interest in biogas. We just submitted another EU proposal where we coordinate, and it's entirely focused on biogas SOFC combination, going for the small scale. And in preparing the proposal, I was in touch with a range of biogas producers, and they're all very interested in the technology, because they say, if you can deliver 60%, and if you don't have the emissions, and there is less maintenance issues, because on the small scale engines have issues, and they are at the 20-25% efficiency, there is really something to make a difference.
Thank you very much, Jan.